Please remember that the standard form of an SDP, a semi-definite program, is this one. You just need to learn it in a way. That's the standard form, you need to know about it. And so I want you to understand that we have here our objective function. Here are constraints. We have three constraints. And so, yeah, you can see those constraints as optimizations themselves. And so, for example, if you take the indicator function of this, it is equal to inf of psi, which is superior to 0, of psi multiplied by ai minus trace of fy of x. So that's about the first one, for the first constraint. And so how can we prove it? The fact is, an indicator function, it just at the end has this form, other constraint here in the current f of x equal 0 if p of x equals true, and minus infinity if p of x is not true. And so the fact is, you just have this, and so here p of x is just trace of fi x inferior to ai, but so if you take this, you see that if you respect the constraint, you have trace of fi of x is inferior to ai, and so yeah, basically the minimum about it would be 0, because you can take psi equals 0 because the number of psi is 0, and so you'll just go into p of x equal true. And if it is not true, then you have like trace of fi of x is superior to ai, and so ai minus trace of fx will be inferior to 0. Because it is not true, then you can just put this to minus infinity, and you'll just get into the other constraint saying that if it is not true, you'll go to minus infinity. Second one is this one, I of the trace of gjx equal bj, and so basically you do the same trick and perform the g leading to r, because this time it's inequality, sorry. And so of lambda g dj minus trace of gj of x, and basically you do the same. You see that if it is true, then you have bg equal trace of gj of x, and so ag minus trace of gj of x will be equal to 0, and so even without fixing lambda, we have directly 0 if p etc. But if it is not true, we'll have this, and so we just can fix lambda g going to minus infinity once again, and so you go into this other case, and so you'll see it's equivalent in a way, it's equal, and you have your optimization. And the last one, which is, well, we can write x here, maybe later, if I accept this, x it's equal to trace of xy, and so it is equivalent because, and you can write it to n of x semi-positive definite. If it is true, indeed you'll have that uh, x will be semi-positive definite, y too, so the trace of xy will be semi-positive definite, and so the inf, like the less you can have is 0, the super is equal to 0, so it will be 0 if p of x equal true, and if it is not, then you have that x is not semi-positive definite, which means that v dagger x v will be, for example, equal to -5. No, it will be inferior to 0, and so if you just take y being equal to v dagger, then I do not remember if it is transpose or dagger, but if you take like, yeah, it's transpose, like if you take like, yeah, if you take the transpose of it, like it will be v transpose this, v transpose v, and so if you take the trace of v transpose v, the trace of xy will be equal to the trace of v transpose vx, and because of the simplicity of the trace, it will be trace of v transpose x v, and so equal to it will be equal to -5, for example. But if you like, yeah, if you just take an alpha, for example, you'd see like y is equal to alpha multiplied by this, then you just have that um, you'll just have this, like you just fix a y alpha here, so you have this, and so you have alpha -5, and you just go to alpha going to infinity, and so you'll just get into minus infinity, and so you'll go into this other case, and you just prove that the three constraints here can be written as optimization themselves, and so you'll see on the next video that it can be really useful to write their SDP, their dual Lagrangian. So yeah.